We're going to go jump over into the PowerPoint. Now, these things were put out there for you the other day, or yes, last night, because I'm working pretty late trying to get some of this stuff done before it's due. So, I don't know why that guy's. Hold on a minute. Let's see if I can get rid of that. It's locked. Okay. All right. So this is out there for you. It's not complete because I still haven't gone deflection on there, and we're not going to take a look at deflection. So again, I just want to jump in and look at some of the nuts and bolts of this stuff, show you run through some problems. There's quite a few example problems I'm going to run through. But remember, this will be pertaining to the stuff that we're going to get into in the final, okay, primarily. So let's go ahead and get started here. So chapter 12 is dealing with what we call beam behavior, and it's going to talk about three major things: bending, shear, and deflection. So what we looked at in chapter 11 was, what happens when you load a beam. And now we're going to look at what happens internally when you load a beam so that it doesn't go to failure. So we'll talk about some things a little bit in the introduction. We'll look at beam behavior in bending. So in other words, we're going to take a look at moment type of stuff first. And like I said, there's a lot of theory that goes with this, and I'm going to kind of reference you to the book on that. I'm not going to spend a lot of time going over the theory. I just want to show you the mechanics of how to do this stuff. And then you can kind of go back and you'll see, you can read through that section yourself and see how that works. Then we're going to look at bending stress today. That's calculating stresses that are involved with beams. And then the last thing we're going to look at is shear stress. So ultimately, this chapter also deals with deflection. So we're going to look at calculating deflection using standard formulas. There's a couple different ways of doing deflection. I am not going to cover deflection today. So we're going to pick up with that on next week's lecture. And then we'll also be starting into the last chapter, chapter 13, okay? So that's kind of where we're headed. All right, so let's take a look. So last week, previous chapter, we looked at forces applied on a beam, whether they're what we would call a point load or a uniformly distributed load. Those things are going to create problems for the beam essentially, and they will develop what are called shear forces and bending moments. So those are caused by those applied loads on your beam. And we looked at ways to determine the magnitude and the distribution of those forces. So we can do a shear distribution and a moment distribution across the length of the beam. And the process that we developed there was, we talked about shear, and we talked about moment, but then we also talked about creating that, what we call the shear moment, the shear and the bending moment diagram. So those are the things that we developed that allow you to determine magnitude at any point along the length of that beam, okay? Stacy, did you have a question?
No.
Okay, all right, so the shear forces that we're talking about and the bending moments are what we call external, because those are due to the applied loads. So what we're going to look at, what's going on in this chapter, is what's happening internally. Okay. So when you have a beam loaded, okay, to offset that shear and the bending, the beam has to develop some kind of internal resistance. And that internal resistance is referred to as a stress, just like we talked about with chapter 8, when you take a rod and you pull it, if it's not going to go past a failure point, it develops a stress internally that resists that force that's being pulled on it. Well, the beam is going to do the same thing, and it has to resist those two types of loadings that are happening to it. One is the shear force, so the thing that's resisting that internal resistance is a shear stress. And the internal resistance to the applied bending moment is what's called a bending or a flexural stress. Okay, so you can use either term there for the moment kind of thing. So bending and shear stresses are going to be extremely important to any designer or engineer. And they're going to need to know, first of all, like we said, where are these points of maximum applied moment and shear, but then we can develop these shear stress concepts. And the other thing that's important, we're going to be talking about this in chapter 13, is in conjunction with these two types of stresses, this bending stress and the shear stress, you're going to have other types of stresses that can be occurring on that beam. So instead of loading it just horizontally, we can load it, or vertically, we can load it horizontally as well. And that will develop another type of stress. So when we have that, we have what's called a combined stress. So that gets a little bit involved when we start looking at combined stresses. And that's probably the crux of what's happening in chapter 13. So we'll come back to this concept of combined stresses in a week. Okay, so when you subject a beam to any kind of vertical force, it will respond by deflecting. And basically what we mean is it's going to kind of push down. So let's see if I can get you a picture here. If you're following along on the book, you can look at your book, but if I can draw a real quick picture, and we did this the other day, if we have a very simply, whoops, let me undo that. If I have a very simply supported beam like that, something like that, and you have loads on this beam, let's say we'll just put it right in the middle. Oops. A little early in the morning yet. So if you have a subjected load here, here's a force, and you got a reaction here, and a reaction here. Naturally, that beam's going to deflect. So what it's going to do is something like this. And this amount, this distance here is what you refer to as your deflection. Okay. So the amount of deflection will be important, as we'll talk about later. But so what you get is in this beam, if you've got a uniform moment, okay, one that like I put right in the middle, that beam is going to deflect along its length, and it will tend to stretch in one direction and compress in the other. So what we have going on there, if you're loading it from the top down, it wants to stretch along the bottom, and it puts that beam in what we would call tension, and it compresses along its top. So we put that in compression. So think of it that what's happening on the bottom, it's stretching on the bottom and squeezing on the top. And you can view that along the whole length of that. And if you do that, then it's referred to as flexural strain. So we say that tension develops along the bottom, causing an elongation, and compression happens on the top, causing a shortening. So again, if we would look at a picture, incrementally what we'd be looking at, and this is kind of a good thing to see here. Let me undo this a minute. So if you think of just an incremental little piece of the beam right here, okay, what we're saying is due to the applied load, there's a point here at which nothing's going to happen. And this is referred to as a neutral axis. But what we're saying is if that thing's truly being pushed down like this due to a bending moment and other things that are causing, what's going on in the top, it's going to shorten like this. So the distance from here to here is elongating, and the distance here to here is compression. So we're saying that this is in tension, the fibers are pulling apart, and here it's in compression. Whoops, let me undo that. So it's compressing up here. So in other words, if we measured this distance, technically there would be shorter than it would down here. But what's happening here is nothing. So that's referred to as your neutral axis. So what we have going on here, we have strain. This is called flexural strain. That strain, remember, is defined as deformation divided by original length. So technically, and it might be not measurable, but we're seeing because of that deflection, that moment, that this is shortening on the top and it's compressing on the bottom, or compressing on the top, so it's shortening, and it's putting it in tension, so it's pulling it apart. So that's what this is talking about here. So that beam, when it's under that uniform moment, it tends to stretch along its bottom fiber, tension, and compress on the top, okay? So with tension on one side and compression on the other side, there is a location where that beam does not strain at all because it has to go from one state to the other. And this is referred to as your neutral axis. So just think that the neutral axis, there's zero strain, so therefore there's zero stress, and also there's zero change in length, okay? So this is the plane that has zero strain. So if there's zero strain, there's going to be zero stress. So because that neutral axis has zero strain, it must also have zero bending stress, okay? So no strain, no stress. And if the beam is homogeneous, so it's made of one material and it's symmetrical, so in other words, you have like a cross section that's a rectangle, the neutral axis will typically coincide with the shape's centroidal axis. So this is where we get back into centroids. If you have a very simple shape, the centroidal axis is going to be where that zero neutral axis point is. If you have a complex shape, such as a T-bar or something like that, you're going to have to calculate where that centroidal axis is. So remember, that might increase up or down depending on what's going on. So moment of inertia is going to become important also as we get into this. Okay, so you're going to see both things come into play here in a bit. Okay. So that strain about a beam's neutral axis occurs in a linear relationship. And so strain will increase as the distance from the neutral axis increases. So strain at the very outside of the beam, both top and bottom, is the largest on the beam's cross section. So again, let's jump over here and see what this is saying graphically, because it's easier to see what that means graphically when you say that it's a linear kind of thing. So again, I'm gonna draw a different picture here. Very similar to what we're just looking at though. So if we see what's happening on the end of a beam here, and let's say this represents the beam's neutral axis right there. Okay. What we're essentially saying is if it's homogeneous and the distance here and the distance here is the same, what you have going on is compression on one side and tension on the other. And we can look at it kind of like that. And what we're seeing here is that if this is pulling this way, whoops, let me undo that, sorry about that. If I'm pulling this way, then I've got, this isn't working too well for me today. So I've got a vector going like this, and like this, and like this, and like this. And then there's vectors going this way on that beam. So this is compression, top, tension in the bottom. So what we're seeing here is this is where you get your linear relationship. Notice as you get, if this is my neutral axis we know nothing's happening. Zero compression, zero tension. This is a point of maximum compression and this is a point of maximum tension. But notice here's your linear relationship. So what's going on is this amount here, if this is an equal distance, it's the same, tension and compression are going to be equal. And notice as you go down, it follows that linear relationship, goes through zero. Okay, so what we're essentially saying, and this is going to be an important principle that we're going to be looking at, the further you get away from the neutral axis, the more compression or tension you're experiencing. Okay, and this is that linear relationship that's following. So that's what we're talking about here, that strain will increase as the distance from the neutral axis increases. So consequently, your bending stress is going to be largest at the very outside fibers of the beam. Okay, that's going to be always true for the most part, unless you have some other combined stress in there going on. So bending stresses, tension and compression, they're going to develop to counteract that applied bending moment by developing a counteracting moment through the creation of what's called a bending moment. So basically, if you remember, a moment is defined as a distance times a force. So the force that's being waged on that is creating a moment, that bending moment, but you're also going to have the beam developing a counteracting moment. And what that does is if it's in equilibrium, then you don't have failure. Okay? So that internal bending moment develops in response to the externally applied moment. So for static equilibrium, they have to be equal. All right, so essentially what you're saying is, again, if we go back to this picture here, essentially what you're saying, there's an applied moment that's bending like this. Well, let's see. This thing's developing a moment. Notice this distance times this force, distance times that force. This is developing an internal moment like this, and there's an applied moment here. So this is your moment applied. This is your moment internal. And for equilibrium, these have to be equal. So you notice that one cancels out the other. Magnitudes are the same, and the direction of those moments are different, opposite. Okay. So that's essentially what we're saying here. So methods that you can use to increase a beam's bending resistance so that they don't go to a failure mode would be things like improve your material composition of your beam. So what you can do, for instance, is change from one material to another, such as wood to steel. So if you were having a problem, with a particular bending moment and wood wasn't getting it, you could maybe go to steel. Okay. And of course, that's talking then getting your modulus of elasticity into play too. So you're looking at a material that has a higher modulus of elasticity, typically, when you're looking at that. If you have a point that that beam is really, really going to be weak in and you still want to use the same material, you might consider bracing that beam at a susceptible point. So wherever it's tending to buckle or bend more, you could brace it. And the main thing, one of the big things we can do is just increase the depth of the beam in cross section. So by doing that, you're increasing the distance from the neutral axis out to the edge. So remember, a moment is directly related to distance times force. So the more that you can get that distance out, the more you can increase that moment. Okay, and it also has to do with the modulus of it, or the moment of inertia. Because remember, moment of inertia is also that guy that's doing resistance to bending. Okay. So there's a couple of equations. The formula basically for calculating bending stress at any location is a very simple equation. Now, on section 12.13 or 3, Tom goes through this bending stress derivation. And you can read that if you want, but at the end, and I would suggest that you do, but on page 376 at the bottom, basically they give you this, what's called your bending stress equation. So it's basically this right here. So your bending stress is going to be equal to the moment, that's your applied moment, times C divided by I. So that's your applied moment. C is your distance from the neutral axis to the edge, fiber, or wherever you're looking at in the beam, divided by the moment of inertia. Okay, so I don't know why my slides are doing that, but okay, so we're going to be taking a look at this equation over the next. I'm going to do a couple of problems with you and just run through this. This equation is really, really easy to use. Okay, that's the good news. The theory of how we got there is because you're starting to develop it from strain and stress and all of that to get to that point. So you can read through that. He does it in those pages, like I said, 374 to 376. But remember, stress is your bending stress. Of course, that's going to be stress units, PSI, KSI, Pascal, kilopascal. We'll do a couple on each. M is your applied bending moment at the cross section. So M is due to your external loading. So that's where you may have to go into a stress strain diagram to determine that if it's not already given. And we're going to do a couple of those problems where you'll see that. C is the distance from the neutral axis to the point of bending stress that you're considering. Normally, C is going to be the distance from the neutral axis out to the edge of the beam, but you might be wanting to look at what's the stress, let's say 3 inches above the neutral axis. Okay, so you might want to do that. So that's kind of it, all right? So we're going to take a look at this. This is called the bending stress or flexural stress formula. Okay, so we call it either one. And excuse me, it can be used for a lot of applications. So if you want to calculate bending stresses that develop in an existing beam or have been developed, if you want to determine moment of inertia required to resist a certain amount of applied moment, this is you can back into this equation and solve for moment of inertia. So those are two good ways of looking at it. And to provide any kind of safe design, usually you have an allowable bending stress value that's given, and you have to work around that. So it's just like any other thing. You have an allowable stress in tension or compression or whatever. We're going to look at the same thing with beams. So we're going to go through some examples out of your book. I'm going to start easy, and we're going to build up. And we're going to start out with problem 12.1. Okay, I'll go through that, and then we will we're going to do quite a few here. Now these are really not very tough, but if you have issues with it, mostly it's kind of a units thing. Okay, so let's jump over. Let me jump over here to my drawing here. I'm going to go through like 4 or 5 problems with you. Okay, and then the last thing we're going to take a look at is shear stress. So we're going to look at bending stress first. Okay. So problem 12.1, they give you a beam in cross section and they show you some dimensions on this. So let me just draw this little picture real quick. So they show this beam in cross section, and this beam, because it's a rectangle, has a centroidal axis like this. Now the other thing, we're not going to be typically looking at 2 centroidal axes, so we're usually looking at loading straight down. So we're assuming that we're loading in this direction, and we're not looking at the length of the beam on this problem. We're looking at its cross section right now. Okay, we will look at length here in a minute. So this is an 8-inch section of this beam, and this is 14 inches. So what we have is 7 inches here and 7 inches here. So the total depth is 14, okay? So what we also know in this problem, that you have an applied moment or applied load that has generated a moment of 150 kip feet. So that moment is the applied moment of a bending moment due to some applied load. You don't even know what the load is because you don't know anything about the span on this one or anything else. So what we want to do is calculate the bending stress at the outside, and we also want to calculate the bending stress at 3 inches from the neutral axis. Okay, so essentially we're going to be using the MC over I equation. So the first thing we're going to want to do is calculate the moment of inertia. So anybody remember what the definition or the equation for moment of inertia is for a rectangle? Anybody tell me? I hope you guys all can. Nobody can tell me that? Nobody?
Isn't it base times height cubed over divided by 12?
You're close. Yeah, you're right. Probably a better way to say that is 1/12 the base times the height cubed. Make sure you're saying the height is cubed, not the base, okay?
Okay.
So which is the base here, Irvin, sorry.
8.
Yeah,
8 inches.
okay, so it's 8. So in this case, we would have 8 times 14 cubed divided by 12. So remember, we're looking at the total cross section here, right? Now, when we consider the bending, we're going to be looking basically in this area, all right? So yeah, that's correct. So let's get that first. That's our first step. And also, we got to really think about units in this. Units is not that tough, but I'm going to show you some things you got to be aware of with this, okay? So I got a syntax here. Hold on a minute. I'll be there in a second. I got 180, 1829. You guys might want to work through these with me so that you know what's going on. Inches to the fourth, okay? So that's my I value. So the bending moment at the extreme outside edge, which would be here or here, is going to be this distance of 7. So the bending moment for the outside is MC over I. Now we have to think about this. The units here should be pounds per square inch or kips per square inch. Notice the unit here is in kip feet, right? So we want to make sure that everything's in the proper unit. This is in inches. C is going to be inches. So this should be kip inches, not kip feet. So basically all we need to do is multiply this by 12. So what I'm going to do is take 150 kip feet and multiply it by 12 to get it into kip inches. Is everybody okay with that? Because that's really important. If you don't do that, your whole problem will be out by a factor of 12. All right? So that's my moment in kip inches. C is the distance from the neutral axis to the outside fiber. Now notice we can go two ways, okay? But it's going to be the same because the distance 7 is the same. And then we're going to divide that by the moment of inertia. Okay, so let's see what we get. It's like we're looking at 6.89, and that would be PSI. I'm sorry, KSI, because this is kips. So that would be kip inches, KSI, okay? So what that's telling me is the stress that has been developed due to a bending moment there was some applied load that put a bending moment of 150 kip feet on this beam. This point would have a resistant bending stress of 6.9 or 6.9, essentially, correct? Okay. Now, if you're looking at this fiber, assuming that we were pushing down this way, this is in compression, so that would be a compressive bending stress. And at the bottom, you would call that a tensile or a tension kind of bending stress. But the compression and the bending would be the same, okay? Because it's the same distance from the neutral axis. Now we're going to look at what's happening here 3 inches from the neutral axis. And again, if we go 3 up or 3 down, it doesn't matter. So this equation just changes like this. You're going to have 150 times 12. C now becomes 3 inches, and the moment of inertia remains the same for that cross section. And so what happens now, it looks like 2.95, and that would be KSI. So what you're noticing is that the stress is going from a max. This is the maximum stress that develops here. It gets less, and then it actually goes to 0. So if you were looking at a diagram of what's going on there, what you're saying is, again, looking at your neutral axis, and this is an important concept with stress because it's going to be an inverse relationship when we get to shear. What we've got going on here is this. It's max, oops. it's maxing, let me try that again. It's maxing here and here, and it's 0 there, and it's linear. So if you'll notice, this will be a linear relationship from the max to that point to 0. Okay, so everybody get the idea? Pretty straightforward.
Yeah.
Now, the only thing you really have to watch is this. This is the thing that I would say that you really got to pay attention. Watch your units of the moment and everything else. Usually you're going to be in inches and inches, or if you're metric, you might be meters and meters. So you got to make sure that everything is correct that way, okay? So we're going to jump to another problem where we have to do all of the work on this one essentially. So what I'm going to do is, let's clean this up. Excuse me. So we're going to have a beam that's simply supported. Now we're going to have to do a diagram on this one. So I'm going to, give me a sec here. I have this guy is loaded. Let's see. Give me a sec. That's not the one I want. Okay, so this one is a beam that is it's a W12 12 by 50. It has a uniform loading across the top. So this guy's got a uniformly distributed load across its top. And that beam is loaded with 2 kips per foot loading. And the span on this thing is 20 feet. And we have a reaction here. I'm going to go ahead and develop something here real quick. And we're going to have a reaction here. But what I'm going to do, we're going to have to develop a shear moment diagram. So that's why I'm putting those lines in there. All right, so there's one reaction. There's another reaction. So what we're going to want to do is determine on this, we're going to want to determine the bending moment, the bending stress rather, at the mid-span and the quarter span points. And we're going to do it at the extreme edge of the fiber, okay? So in order to do this problem, we're going to have to solve the reactions, then we're going to have to solve the shear, then ultimately we're going to have to solve the moment, okay? So can anybody tell me what the reactions are right now? You can do this pretty much by inspection. How many kips is each reaction taking? No one? Well, we have a 20-foot span, right? This guy's uniformly loaded, so we can replace that with a point load that would be 20 times 2, place it right in the middle. So if you essentially have 40 kips coming right down in the middle of the beam, what does that mean each one of these is carrying? "20 is dead center, or 40 is dead center. How much is each reaction taking?" Has to be half. So if you run through the statics on this, we should find that this is 20 kips here and 20 kips here. Okay, so I'm going to go ahead and put that in. That really doesn't exist like that. That was just how we modeled it. Okay, so let's go in and we're going to do a shear diagram first. Hopefully you guys remember how to do that. So we've got a shear diagram, and we're going to have a moment diagram. Okay. Okay, so who can tell me what's going on in the shear? We're starting out with 20 kips of shear, so what does that mean for our shear? That we're coming up 20? So we have a shear force here of 20 kips. What's happening as we step across this beam with a 2-kip load? What's happening to the shear? Is it staying constant or is it dropping? Nobody can tell.
Isn't it just staying constant?
It isn't, because constant would mean there's no load happening up here. Isn't there a load going on as you're stepping across it, Max?
Yeah.
Okay, so what it's doing is it's dropping, and it's dropping at a uniform rate. So what's happening is it's really doing this. It's really just starting here, and it's going to end down here like that. And then this is going to go back up to 20. All right. You guys see that now?
Yeah.
Okay, so as we step across, notice that's just dropping, and it has to drop from 20 to a negative 20. And it has to go to a negative 20 because when we add these two together, it has to go back to what? 0, right? So we have two areas here, area 1 and area 2. This thing is crossing 0 at some point, which happens to be mid-span. So what does that indicate for us when you're crossing 0? What's that do to the moment? When you cross 0 at the shear, you get another critical line developing. What's happening at that critical line?
Peak.
Right, you're getting a max on the moment, correct, okay? Now, if you guys remember, if you have this kind of thing going on, you got a parabola developing. So what's happening is I'm not gonna be able to draw this very well, I don't think, but what we essentially have is a parabola that's going to come up, it's going to start at 0, it's going to peak, and then it's going to go back down. So this is a real symmetric parabola, and we're going to have a maximum point right here. So how do we solve that max point? Isn't the point at any point on my moment diagram related to the area under the shear, right? So we have an area here. This area is going to be 20 times this distance, which happens to be 10, because that's the midpoint. So that area is going to be 20 times 10 times 1/2. So we get 100 kip feet of maximum moment at the middle of the span. Okay. Now we're also going to look at the quarter points, so we're going to see that too. All right. Then this one has to go back to 0. So if you notice, if you take 10 times 20 negative times 1/2 and add that, you're going to get back to 0. Okay. This is where the moment diagrams kick in. All right, so we want to know, what is the bending stress on this beam at midspan? So that's MC over I. Now we just determined M, okay? But we need to determine C and we need to get I. So where do we get that information from?
Back of the book.
Yes, okay, so we're gonna go back to Appendix A. Appendix A, this is a 12 by 50. So this is a nice lookup, and we only have to worry about we're only worried about the moment in one direction, okay? So We're looking at the XX for the moment of inertia. So what'd you get for a 12 by 50? Anybody get me a number? 12 by 50 for the XX axis moment of inertia. I got 391 inches to the fourth. Does that look right?
Yeah, that's good.
Okay, the other thing we need is the depth. That's the distance from the top flange to the bottom flange. Okay, that depth. So we're looking for D on that chart. Looks like
12.2.
Yes, correct. That's what I got. Now that's important because that's going to allow us to get the C value. Okay, so if we looked at this in cross section, what we're looking at that in that I-beam is this. We've got that, and we've got that, and we've got that, and we know the moment of inertia. The neutral axis is right there. Whoops, the neutral axis is here. So this distance is half of D, and this distance will be half of D, okay? That's why that's important, okay? So calculating the maximum moment, or at the half point, we would say midspan, the moment is 100 kip feet, but these are in inches, remember, so we're going to convert this to inches. So that's going to give me kip inches, okay? C would be what? The distance from the neutral axis to the edge fiber of this beam. So what would that be? Half of the depth. So that's C for this one. And then the moment of inertia is 391. So let's see what's going on. Anybody get an answer? I got 18.2 kips per square inch. Does that sound right?
Yeah, that's good.
Okay, so that's saying this is the point of maximum moment. That's your applied maximum moment, 100 kip feet. So the bending stress that needs to develop in that beam has to be 18.72 kips per square inch. If you would exceed that, that beam would fail, essentially. Although we have to take into other things, there might be an allowable stress, so that may not even be near the allowable stress, but we're looking at that. We have to make sure that we can maintain that. So he also wants to know what's happening at the quarter point. So the quarter point would essentially be here. So we need to know what is that point right there. So to get the quarter point, let me erase some of this. I need to know what this elevation is, or basically that height on that slope line. So if this is 20 and that's 0, and this is 10 and this is now 5, yeah, erase this. We're looking at a distance now of 5 feet to here. What would that point be? 20 and 10 is going to be equal to x and 5, essentially. So what that gives me is this is going to be 10 kips a shear. So we now have a trapezoid that we can use to solve this point right here, okay? So that moment at the quarter point is going to be equal to 20 plus 10 divided by 2. Okay, so that's the average height over the distance that it's acting, which is 5. So let's see what we come up with there. Looks like 75 kip feet. So what we're saying is this is going from 0 to 75 to 100, and it's doing that parabolically, and it's going to drop at the same rate. So the quarter point and the 3/4 point, if we're going left to right, is going to be the same number, okay? And if you solve the stress here, it would be 0 because there is no bending stress. So the bending stress for the quarter point is going to be the bending moment, which is 100, and times 12 to convert that into kip inches. And then it's going to be that same C value, half of the distance of the depth. I'm sorry, it's not 100. I made a mistake. It's 75, because we're looking at the bending moment at the quarter point. 75 times 12 times C, which C stays the same. And we're going to divide that by 391. So it looks like I'm getting 14.04, and that would be kips per square inch. Okay. So what we would see here is if you started here, 0 moment would give you 0 stress. As you go across the beam, now you're at 14.04. It's going to max out here to 18.72, and then it's going to drop to 14.04 and back to 0. So this was an application of having to calculate your bending moment as well as doing other things, okay? So we're going to look at another example, and this one's going to be a metric example. So let me clean up my screen. Does anybody have any questions so far? Does it seem pretty straightforward?
When you like took the 10 times 20 and divided by 2, how did you get the, or what, it
You're
was,
talking about up here, Jake?
yeah, where did
Okay.
divided by 2 come from?
Okay, because this is a trapezoidal area right here.
Okay, all right.
Because the area of a trapezoid is going to be half of the sum of that. In other words, what you're calculating is this side plus this side divided by 2 gives me the average height, basically
Okay.
right there. So the average height times the base gives me that. So this is just the area of a trapezoid. Now you could do that another way if you wanted to spend more time. You could break this down into a rectangle, which would be 5 times 10 right here. And then you have this little triangle that would be left here. So that would be 10 times 5 times 1/2. So those added together should give you the same number. This is an easier way of doing it, though, if you calculate that trapezoid using average heights.
Okay.
Does that make sense now?
Yeah, I see it now.
Okay, cool. All right, any other questions? All right, we're going to look at a third example. This is a simply supported beam, but it also has a very simple loading scheme on it. But we're going to have to develop a shear moment diagram, and you're going to see it's a nice thing. It's going to show you different methodology or difference in how we're doing it. So let me clean this up. Are we okay before I move on? We good?
Yeah.
Okay. So I'm going to generate a new diagram here. And so in this one, we have a very simply supported beam also. This one does happen to be metric, so that doesn't really change anything, just means you have to deal with metric issues. So again, we're going to have to develop a shear moment diagram on this. So I'm going to just go ahead and put the lines down here. Oh, I forgot to mention, by the way, I have a diagram that I developed for you guys for your shear moment diagram, so you can determine whether it's parabolic or that kind of stuff. So I'll bring that with me on Thursday. But you won't need that for the test, remember. Hold on a minute. Okay, that worked. That worked. All right, let's see. Let me look at the cross section. We're going to have a cross section over here too, a beam and cross section. So this is a big picture, and it's going to be a rectangular. It's going to be a rectangular section. So we're going to be looking at that right there. Okay, so this has simply supported. So we're going to have a reaction here. We're going to have a reaction here. It's loaded with 20 kilonewtons of load. This load is right in the middle, so it's 5 meters and 5 meters. This guy is 300 millimeters by 600 millimeters total. And this guy's my neutral axis, okay? That's my neutral axis. All right, so let's start out. Who can tell me what the reactions are, left and right? You got a load of 10 kilonewtons right in the middle. What's going to be true about the reactions? That should be pretty simple.
5 on each side.
Exactly. It's got to be carrying the same amount because it's an equal distribution, right? So we got 5 kilonewtons and 5 kilonewtons. Now, there's problems are not always going to be that easy. So, you know, that just happens to be for this example. All right, so I'm going to develop a shear and a moment. Do we have all the critical lines down that we need for this diagram? Critical line at the reactions.
How about, should there be
And then
one at the 10 kips?
There should
Yeah.
be kilonewtons.
Yeah.
Yeah, you're right. You just said kips, that's all.
Oh, yeah.
Okay. All right, so yeah, we have 3 critical lines that have developed, okay? Now this guy's gonna be real symmetric. So let's go ahead and we'll look at shear. We're gonna start out with 5 kilonewtons, whoops, 5 kilonewtons of shear. Hold on a minute. It's not working for me, right? Okay, 5 kilonewtons of shear. Now, what's true about that shear as we step across this beam? Changing or constant?
Constant.
It's constant. So this one, max is constant, right? Then we hit 10 kilonewtons going down. So 10 minus, 5 minus 10 gives us a negative 5. And then it's going to be what? Constant across until we hit the reaction, and then it's got to go back up to 0, okay? So this is going to be negative 5. So we have 2 areas here, area 1 and area 2. Whoops. So this, because of this is rectangular, what's going to happen with your moment? You got to remember that we talked about that the other day. The moment is going to be linear up and linear down. And it has to start at 0 and end at 0, right? So to solve that peak, we know that that peak easy, buddy. That peak is going to be the area of this. So this is going to be 5 times 5. So 5 times 5 gives us 25 kilonewton meters at that point. Okay. Is everybody good with that?
Yep.
Area, 5 kilonewtons times 5 meters gives me 25 kilonewton meters. We're okay?
Yeah.
Yeah.
Okay, so we want to get everything in meters in this one. All right, so we could convert that to millimeters, but that would be a huge number. So it's probably going to be better converting these to meters. So this would be, if we take, what, 300, right, and divide it by 1,000, we get 0.3. And this one's going to be 0.6. And that is meters. So we need that because we want to solve I for this. So I is 1/12 the base. The base is 0.3 times the height, which is 0.6 cubed divided by 12. Okay, let's see what we come up with there. I get 0.0054 meters to the fourth. Does that look right?
Yeah.
Okay, so if we're looking for the bending stress at the maximum point of moment, which is mid-span, then the bending stress is MC over I. We just determined the bending stress to be 25 kilonewton meters. We're going to multiply that by the distance from here out. So that's going to be half of that. So that's going to be 0.3. Make sure you know that this is 0.3 because it's half of the distance, not because it's that direction, okay? So that's in meters. And also then we're going to divide that by the moment of inertia that we came up with, and we'll see what we come up with here, okay? So we get, let me think. What'd you guys come up with? 1388.9. 1388.9. What would be the unit of that? Kilonewtons per meter squared. Kilonewton per meter squared. What's another way of saying a kilonewton per meter squared? Another way of relating that would be a kilopascal. So you could call it a kilopascal. So you might see answers sometimes in this. These are the same thing. Okay? So this is the point of maximum bending stress that has developed at mid-span. What if we wanted to go in here and look at quarter span? So if we wanted to look here at that point, so now we're talking about a distance of 2.5 meters, okay? So we need to solve this point on that moment diagram, but all we have to do is calculate the area up here, okay? So the area would be 5 kilonewtons times 2.5 meters. And it's linear, so you could also look at it being a linear relationship, but that gives me 12.5 kilonewton meters. So the bending moment at the quarter point on that is going to be MC over I. In this case, the M has dropped to 12.5 C stays the same because we're looking at the extreme edge fiber and 0. So that gives me that. I'm not having success with my calculator today. It's like 694.4 if I did that right. And you could call that kilopascals. So there's one answer, there's another answer. Notice from a linear standpoint, your bending stress is going from 0 to a max of 1388.9, and then it's going to drop back down to 0. Okay. Any questions on that one? Okay, we're going to do one more then. This one's a little bit more convoluted. It's going to be a complex, what we call a T-beam. Okay. Is it, before I move on, is this okay for everybody?
Yeah.
Okay. Is it pretty, it's pretty straightforward, isn't it?
Yeah.
The only thing you got to remember is units. So just got to watch your units in this equation. And also, of course, you have to know how to do this. If you can't do your shear moment diagram, you know, then that's related. So you can see why this, we don't want to put this on this test because this will be relate to what we'll be doing on the final and next test. So, okay. So I'm going to create a new diagram and let me explain what's going on. We have a T-beam, which basically just has basically two rectangles. So one's kind of like this, and then one is kind of like this, as long as I can get that pretty. So there's symmetry going on here between those two. On this one, we don't know where the centroidal axis is, so we're going to have to determine that. We do know a couple things. That this T-beam is 8 inches and 2 inches this way. It's 2 inches here, and it's 10 inches here. So what we're looking for is where is the y bar distance, or what we're really looking for is the neutral axis. So where's the neutral axis on this thing? And it's going to be, I'm just going to kind of eyeball it in. It's going to be somewhere about like there. We also know that this guy's going to have an applied moment on it. So we don't have to calculate the moment in this equation. The moment's already been, it's already been calculated by somebody. So the applied moment they're giving you in this problem is 200 kips feet, 200 kip feet. So we want to know what is happening at this edge of the beam and what's happening at that edge of the beam in terms of your bending stresses, okay? So what we have to do is go back to centroids first. We have to figure out the centroidal axis, and then we're going to have to figure out the moment of inertia. So I'm going to call this guy 1 and this guy 2 for shapes. So for my centroid, I'm going to have shape, area. Now I don't need the X bar, so all I'm looking is at Y, and then I'm going to have an AY. Okay. So we're only looking at this direction. We're not looking at anything else. And we can assume we're just coming, oops, let me do this. Let me give it a better line here. We can assume that we're coming from this edge, okay? So what we're after is going to be ultimately this guy when we get done with this. All right. So we don't have to solve both the X and the Y directions, just the Y direction. So for shape 1 and shape 2, we have an area of shape 1 that's 2 times 8. That gets me 16. And then for shape 2, we have 2 times 10. That gets me 20. Everybody okay so far? That's pretty straightforward. So if we're working off of an origin down here, to shape 1's Y, it's going to be the distance from here, which is going to be 10, plus the distance to his centroid, which would be what, half of 2. So this is going to be 10 plus 1 gives me 11 here. So then we're going to have 16 times 11 gives us 176. You guys agree with that so far? 176. And that would be inches to the third. So who can tell me what the y value from the origin up would be to shape 2? What would we have there? Wouldn't it just be half of 10? 5 up?
Yep.
Okay, so we've got 5 for y. 5 times 20 gives us 100. So we're going to sum that, 276. We're going to sum that, 36. So our y bar is going to be the sum of 276 divided by 36. And let me put that over here because I'm going to need some room. 276 divided by 36. I think you can start to see how all this stuff that we've been talking about over the last couple of weeks is now starting to come into play. So if you have to revisit some of this, make sure that you do, because you'll need to get into this as you get into a little bit later. And so I got 276 divided by 36. Looks like 7.67 inches. So that's going to give me the neutral axis here, 7.67 inches from the bottom up. Does everybody agree with that?
Yep.
So now we need to do a moment of inertia, okay? So we're going to do the moment of inertia about this axis here. So again, we're going to have shape. We're going to have I, Y. Actually, it's going to be the XC. We're going to have the area. We're going to have the distance, then AD squared, then ultimately the IXX guy. Okay, so for shape 1 and shape 2, if we look at shape 1, this would be 1/12 the base times the height cubed. Okay, so 1/12 the base, so 8 times 2 cubed divided by 12. I come up with 5.333. You guys okay with that number?
Yeah.
So the area is the same area we had here, right? So we got 16 here. D is the distance from this axis to that axis. So if we go back in here, we noticed that this was 11 to that axis, and this is 77.6 or 7.67. So the distance between those two guys is just going to be 11 minus the 7.67. So I got 3.33. You guys catching that? And we'll square that and multiply that by the area. So we're using that parallel axis theorem to do this. It looks like let's see, 177.42 plus the 5.33 gives us 182.75. Okay, 182.75. All right, does that sound good? So we now have to consider shape 2. So shape 2, his moment of inertia just to that shape is 1/12 the base times the height cubed. So the base is 2, the height is 10. So 10 cubed times 2 divided by 12 gives us 166.67. Notice, because we're assuming it's oriented this way with a load, this guy is bringing more stiffness than that, and that should make sense as the stuff we talked about in the past. So 20 is the area. So we're going to take this distance now. This distance will be shape 2's centroidal axis minus this centroidal axis. So it's 5 minus the 7.67. So 5 minus 7.67 gives us a distance of 2.67. So that is the distance down to that one, and the other one's the distance up. So we're going to square that and multiply that by 20. And it looks like 142. 142.58, I'm going to call it. And we're going to add to that the 166.67. I blew that one. 142. Is everybody getting my numbers, by the way, before we go on?
Yeah.
So I'm coming up with 309.25. And then we sum that to get the total. Basically, you're just coming up with 492. And that would be inches to the fourth. The larger issue here, guys, is that the harder part was getting your centroidal axis, your neutral axis, and also then solving I. The rest of it's just a piece of cake now at this point. Does everybody understand where all this came from? That was chapter 6 and chapter 7 material, right? So we want the bending stress here, and we want the bending stress here. Now, they're not going to be the same. Does anybody know why they're not going to be the same? Why is the stress here going to be different than the stress here? Because the distance from here to here is different than it is from here to here. Okay. So let's calculate it. The bending stress, we'll call that at the top. This being the top is MC over I. What's changing in that equation for both scenarios is that C is changing. That's the thing that's changing. So we have M is 200 kip feet. To put that in kip inches, we're going to multiply that by 12. C is the distance from here to here. So if we have 10 plus 2, that would be 12 minus 7.67. So C for this guy is 4.33. So the distance is 12. The total distance here was 12 minus the 7.67 gives us a distance from here to the outside edge of 433. Are you guys agreeing with that? And then we're dividing that by I. So if we just solve that equation, 4.33 times 12 times 200 divided by 492, we get 21.12 KSI. Assuming we're pushing down like this, is that compression or tension? Can anybody tell me? Compression at the top? or tension at the top.
Compression.
It's compression. So this would be a compressive stress, that's correct. Now at the bottom, use the same equation, MC over I. The only thing that's changing in that is C, the distance from the neutral axis down to the extreme edge of your beam. And that's going to be 767. And what we have is 492. So what we would have there is 200 times 12 times 7.67 divided by 492. And we see that we get a larger amount of tensile. So that's in tension. That's in tension. Okay, any questions on that? Again, this equation, pretty straightforward. Just recognize what's M, C, and I. And the larger part of this whole problem was solving your I value. Okay, we're going to do one more, and then we're going to take a look at shear. Okay, any questions before we move on? Everybody okay? Absorbing this?
Yeah.
Okay, so I'm going to go do one more problem, then we're going to come back and take a look at shear, and that'll finish us up for the day. Okay, so we're going to find, we need to find a value, a width for a rectangle that has an applied moment on it. Okay, so here's what we're going to do. We're going to kind of back, this is going to be a problem where we're going to kind of back into it. So we got this beam out there, and you know, it could be wood, it could be it's probably wood more realistically. But we're going to say we got a neutral axis right here. We don't know what the width is, but we do know that this is a 12-inch depth. So it's 6 inches and 6 inches from the neutral axis. Okay. We have an applied load on this that has generated a moment, a bending moment on this thing of 10 kip feet. So there's applied load somewhere on this beam that has generated a 10 kip foot load, or where we'll assume that's the maximum moment. Okay. And we know also that this has an allowable bending moment of 1.5 or 1.5 kips square inches. Yeah, 1.5 KSI. Okay. So we're given this. Somebody has figured out your maximum bending moment. You know that your allowable is this, so you cannot exceed that. We need to come up with a width of this beam that will not allow that to be exceeded. Okay, so you're kind of backing into this. So what we can do here is we know that bending moment, right, is equal to MC over I. And we know bending moment, we know allowable, and we know C. So what we can actually solve for in this is I. So that would allow us to solve for I by taking this. Correct? So bending moment applied is 10 kips per foot, so we want to get that in inches. C is going to be 6, because we're going out to the maximum. And the allowable bending moment is 1.5 KSI, so it's already in KSI. So KSI divided by KSI cancels, and you're going to be left in inches. Actually, let's see. You should be inches to the fourth. Let me think this through. Moment. This is kips per square inch. That's per square inch. Yeah, so it goes to the fourth. Okay. Okay, so let's see what we come up with. Okay, so I get 480 inches to the fourth. And again, this is in inches, and this is going to be in inches. And yeah, and then that's kips per square inch. So square inches times square inches gives us inches to the fourth. So we know that I has to be 480 inches to the fourth. So if we look at this, we know that I is equal to 1/12 the base times the height cubed. In this case, base is W. So what I can do is solve that equation for the base. So that would give me the base, which we're also saying is W, is going to be equal to 12 times I divided by H cubed. So what that gives us is 12 times 480 divided by the height would be 12, in this case cubed. Let's see what we come up with. If you follow my math, we get 3.33 inches. So the minimum width on this guy that could sustain that load applied bending moment with that allowable would be 3.33 inches, which you probably wouldn't find a board that, so you probably go to a higher one, like maybe 4 inches. So 4 would be fine because 4 would give you a higher moment of inertia. Okay. Any questions on that one? That's kind of backing into it, and that's kind of what a designer might use to solve a typical problem like this. Okay, questions? All right, so we're going to go back. Let's tackle one more thing, and we're going to look at shear stress. So besides your applied bending moment, a beam is also going to have that ability to resist shear forces. So we know that shear forces along a beam are generated by those applied loads, and what they try to do is take that beam and rip it apart. Okay, it's a ripping kind of process. So shear forces have to be developed in that beam to resist that so that you don't have failure. And so that externally applied shear force develops an internally developed shear stress, and it has to be equal and opposite. So the mechanism used to do that is achieved by creating a shear stress, and that shear stress then that developed vertically also will develop a horizontal shear stress along shear planes so that you get equilibrium. And there's a third, you'll also get a vertical shear or a diagonal shear that we talked about that can be important to members like concrete. So concrete can fail pretty readily in diagonal shear, so that's important. So the horizontal shear stress resists the horizontal forces that tend to cause what we call slippings within the beam. And there's a good diagram on that concept of slipping. And if Let me show you what I mean by that. Let me go back to this real quick. So if you envision planks of wood just sitting on top of each other like this, and they're not rigidly affixed to each other, you just have a bunch of, let's say, 2 by 12 sitting on top of each other. And you put a load down on these things like this. What's going to happen is when you load it, whoops, they're going to slip. So the one, hold on a minute, guys, sorry about that. The one's going to slip past the other like that. But in a case where you have a rigidly homogeneous beam, that slipping is going to be resisted by horizontal shear forces within it. Okay. So what we have is the equation that we're going to generate here to calculate shear stress at any location across section. This is called the general shear equation. So it says that your shear stress, sigma V, is going to be your shear force times what's called your area, your static area, divided by I, which is moment of inertia, and B is the distance along your neutral axis. Okay, so you have shear stress, which is going to be typical units. V is your applied shear force in your cross section. Q is the hardest thing we're going to look at. It's called their static moment of area with respect to a centroidal axis. So we do have to look at that. That's actually the hardest thing to deal with when you get into shear, is that static moment of area. And then you have the cross section's moment of inertia, and then B is the width of the beam at the location under consideration. So primarily that is the width of the beam at the neutral axis. So let's look at Q. That static moment of area is considered the first moment of area of a beam lying above the plane where that shear stress is being calculated. And it's basically calculated by multiplying the area above the plane where that shear stress is desired times the distance through the neutral axis. And basically you're just saying Q is equal to your area times D, but it gets a little convoluted. We'll take a look at that. So area is your plane where your shear stress is being calculated. D is your distance from your neutral axis to the centroid of that area. Okay, so when you have complex shapes, you have to break that down. So you're going to have to break that down into simple shapes. You're going to have to calculate an area of static moment for each individual area, and then you sum them. So you come up with this. Q total is going to be Q1 plus Q2 plus whatever. Okay, you get into. All right, so we're going to look at a couple of examples. First off, let me show you what I mean by static area, and then we'll do a problem or two doing shear. And by and large, shear isn't hard either. I think moment is a lot easier to calculate, bending, stress. But with this, what we're going to look at is show you how we calculate Q. So if this is a thing we're looking at, and this is the neutral axis. So if we're looking at the shear stress up in here, so we're looking at this area here. This is my area, okay? This would be, let's say, 3, whoops. If I was looking at this and I give it some numbers, if this was 3 inches and this is 6 inches, Q is going to be A times D, where A is going to be 3 times 6. Okay, so it would be this area right here. And then we need the distance from the neutral axis up to the centroid of that area. Now, the centroid of that area would just simply be 3. So in this case, that area would be 3 times 3 times 6. So you would have 54, and it's not a conventional area. So it's not the area in the sense that it's area times a distance. So your actual unit of this is inches to the third. Okay. So that's what we would call a very simplistic Q. Now let's back up on that a minute. I'm going to erase some stuff out of here. Let's assume you are looking to calculate a Q, a static moment of area, but you're not looking at the total area, you're just looking at a piece of area here. So let's say we're going to look at, let me draw another line here. Let's say we want to consider this area right here. And we know that this distance, we're coming 3 inches above the neutral axis now. So that's 3 inches. So if we're calculating the Q area here, Q is going to be equal to A times D again. A in this case is going to be 3 times this distance that's remaining, which is 3. So 3 times 3. The distance from the neutral axis to the centroid of that area is going to be 3 plus half of 3. So this would be 4.5. So in this case, you would have 4.5. And you would have 40.5 inches to the third. So you don't very often do this kind of thing, but it's just important to know because some of these problems are going to tell you to look at the total distance of the neutral axis. Sometimes they're going to say 3 inches, but what we're calculating is the shear in this area. What you're going to find with shear, what's is kind of important, what we just went through is we found out that the bending moment at the neutral axis is 0, but the bending stress at the edge fiber of your beam is going to be a max. It's going to be reverse at shear. At shear, it's going to be 0 at the edge fiber, and it's going to be max at the neutral axis. So that's why you'd be considering this total area. If you have complex shapes of areas, what you have to do is calculate several different areas. So let me show you that real quick, and then we'll jump in and we'll do a couple of problems. So if you had like that T-bar example we were just looking at, let's say you had a shape that was like this. To calculate, and let's say this actually was our neutral axis here. That's my neutral axis. So if I wanted to get the Q of this shape, I would have area 1 and area 2. So I would calculate the Q1. So that would be area 1 times this distance here. From the neutral axis to the centroidal axis, we'll call that distance 1. And then for area 2, Q2, I would take area 2, which would be this guy's right here, times the distance from the neutral axis to the centroidal axis of that point. And that would be D2. This would be D2. So your Q total in this case would be Q1 plus Q2. I know this probably seems really confusing at first. You're going to see it gets easier, but this guy is the hardest thing to deal with in shear. Other than that, it's not that big of a deal. All right, so let's take a look. I'm going to give you a couple of examples in shear, and then we'll see if there's any other questions, and we'll call it a day. Okay. So let me clean this up. So we're going to start out with a simple problem. We want to calculate the shear in a simple beam. So the cross section of that beam looks like this. Very simple beam. And we're going to have a neutral axis in cross section right in the middle. So that's my neutral axis. This beam is 6 inches this side, and its depth is 10, so we have 5 and 5. So it's 10 this way, 6 that way. The shear that has been calculated at this is 50,000 pounds. So that's a given. That's your total amount of shear that we're looking at. And we want to calculate the shear. We want to know the shear stress at the neutral axis. And we also want to know what it is 3 inches from your neutral axis. And if you calculated it out here, it's going to be 0 because your static moment of area is going to go to 0. Okay, so the first thing we need is the I. So moment of inertia, 1/12 the base times the height cubed. So the base is 6, height is 10, because we're looking at the total. So we get a moment of inertia there. So I get 500 inches to the 4th. Everybody okay with that? We agree?
Yeah.
Okay, so we're going to look at this area right here first. Okay, so we need the Q for that area. So Q is going to be this area right here, which will be 6 times 5. And then the distance from the neutral axis up to the centroid of this, well, that's just half of 5, right? So we get 2.5. So what that gives us is 6 times 5 times 2.5. We get 75 inches to the 3rd. So to now solve the bending stress at the neutral axis, or the shear stress, you go back to that equation. It's VQ divided by IB. So V, 50,000 pounds, times Q, 75. I is 500 inches to the 4th. So keep in mind, this is inches to the 3rd, inches to the 4th, and B is the distance at the neutral axis, so that's just 6. So what you wind up with is inches to the 3rd divided by inches to the 5th. So that's going to give you inches squared. So it's going to be pounds per square inch. So let's see what we come up with. I get 12,500 PSI. So this is the stress that is developing due to the shear that has been developed due to the load. So if you had an allowable shear stress of, let's say, 1,300 PSI, you would be okay because this is below that, okay, under this loading that's producing that. So everybody okay with that? So the second question then is to look at this when they just want to look at what's going on when we're looking at a different cross section. So for instance, not so much a cross section, but a different load area. So they're saying now we want to come up 3 inches. And we want to look at what's going on in this point right here. What's going on in this region, amount of shear. So the Q for that, if this is 3 inches up, we're looking at 3 inches from the neutral axis. My area is now 6 times 2. So Q is going to be area times D. Area is going to be 6. This distance times this distance, which will be 2, times the distance from the neutral axis to the centroidal axis of this shape. Well, if this is 2, this has to be 1. 1 plus 3 gives us 4. So what we'll get there, 2 times 4 times 6. We get 48 inches to the third. So for the bending, or not the bending, the stress at the shear stress, again, is going to be V, Q, I, B. So the only thing that changes here is Q. So again, we're going to have 50,000 times 48 divided by 500 times 6, because this is still 6 here. Okay, let's see what we get here. So it looks like we're getting 800 psi of shear stress that's developed here. So here's what's happening. If you look at this point, at the point of the neutral axis, that area's total area, you're getting, that's your maximum amount of shear stress. As we're looking at less and less areas, this is approaching 0. So this is going to go from their maximum to a 0 point. It's also maximum to 0. Now keep in mind, again, what we said before is that as you go in bending stress, it's reverse. So shear stress is max. Shear stress is max at the neutral axis, 0 at the edge fiber, and bending is reverse. All right, we'll say more about this actually as we get into some of this stuff. So, okay, does anybody have any questions? All right, so we're going to do one more problem, and then we'll just make sure that everybody's good for our test on Thursday, and then we'll knock off. So we're going to do one more problem. This is going to be a W. We're looking at a W channel that is, or I-beam that is 16 by 77. Now we're just looking at the half piece of this, so I'm going to just sketch half of it. We're going to have to go to the charts to get some information for this. Okay, so this is my neutral axis. Oops, that's not. This is my neutral axis of this guy right here. So it mirror images on the other side of this. Okay. So because this is a W 16 by 77, we can look up pieces of information. Oh, we also know that the maximum shear that is being applied on this is 100 kips. So this is a given. Let me do that a little bit better. It was really messy. So V is 100 kips. We need to look up I. Okay, so we need to look up I. So let's go back to the back of the book here. Looking at Appendix A. In Appendix A, let's see what we come up with. So we're looking at that 16 by 77. Looks like that's on page 598. 598. Does anybody see what the I is for that? Page 598. We're looking in the XX axis. I'm getting 1110 inches to the fourth. Now we're going to need a lot of other dimensions. So one of the dimensions we're going to need is this guy here. That will be our flange width. So that turns out to be 10.3 inches. This guy here, which is our flange thickness. Our flange thickness is 0.760. The web thickness is 0.455, and these are all in inches. I'm getting that all from that chart 598. The only other thing I need to know is what is the distance. What's the distance from here to here? That's going to be half of your depth. So the depth for this, the depth is 16.5. So this is going to be 8.25. Yeah, so I needed all of that information because I needed to be able to calculate areas. Okay. Did everybody catch where I got all these numbers from? This is your flange width, flange thickness. This is your web thickness. This number is coming from half of your depth. Oops. Okay, so to calculate this in this area, I'm going to have two areas here. I'm going to have an area 2 and an area 1. The reason I have to deal with that is because I've got to calculate Q. So Q1 is going to be equal to area 1 times D1. So area is going to be this distance times this distance. So it's going to be 10.3 times 0.760. The distance from the neutral axis to the centroid of this would be half of this minus the 825. So we got 0.76 divided by 2 gives me 0.38 minus 8.25. 787. Just check that. 0.76 divided by 2 minus 8.25. Yep, 787. So this Q for this area right here, that Q, that static moment of area, 10.3 times 0.76 times 787. So we get 61.606 inches to the third. Q for 2 will be area 2 plus distance 2. So we're going to have this distance here. That would be 8.25 minus 0.76. Okay, so that gives me 749 times the 455, and we're going to go to the distance of this guy's half of that point. So you're going to take 8.25 minus the 0.76 it gets me 7.49 from here to here, and half of that is the distance to the centroid from the neutral axis. So you guys check my numbers. I got 12.763 inches to the third. Is anybody getting my numbers? So for this area, we took that distance times the distance from the neutral axis to the centroid point. And for this one, we're taking this distance times that distance times the centroid. So Q is actually going to be Q1 plus Q2. So all we're doing is adding those Q's. Basically, that's your amount of resistant area. So we're looking at a total Q of 74.37, we'll call it. Okay, so for this, the shear stress is VQ divided by IB. So V is 100 kips, that's given. Q we just calculated, 74.37. I we looked up, and B is the distance right here that we're dealing with right at the neutral axis. So that is 0.455. So when we solve that, let's see what we come up with. Looks like I'm getting about 14.7 kips per square inch. So that's the shear stress that's being developed in that I-beam for a shear force of 100 kips, and you would probably assume that's max. Okay, we covered a lot of equations, but the equations are pretty simple. The hardest thing in shear is this Q aspect, and we're going to be working on that a lot more. Okay. So let me go back here and see if there's any questions. I am not going to talk about deflection today. And obviously we're going to be revisiting this stuff next week. So our focus for this week then is to finalize your lab. Okay, so that'll be due. That lab will be due on Thursday, and then we'll be looking at our test over Chapter 8, Chapter 9. And remember, I modified that, okay, for those of you that weren't here earlier. I modified the test so that we're just going to be looking at Chapter 8, Chapter 9. You can count on probably 2 problems from each chapter, but there's 4 problems total, okay? Create yourself a cheat sheet, you know, an 8.5 by 11 size piece of paper. You're not going to be responsible for constants. So if you need modulus of elasticity or coefficient linear expansion, all of that stuff's going to be given, okay? And I want you to look over stuff in Chapter 8, Chapter 9. We can do a few problems before the test. Don't worry about Chapter 11, and we'll be good to go. Does anybody have any questions?
No.
You know, there's a lot to digest here, but like I said, we're going to be working in this over the next couple of weeks. So, because you're going to see this again in Chapter 13 as well. So we'll have some time to deal with it. So let's concentrate on Chapter 8, Chapter 9 stuff. Maybe you can look at some stuff on 11. But I probably would think I want to do no more than maybe an hour Monday or a Thursday rather, so that we can get started on that test. Okay. I'd like to give you at least 2 hours, but 2.5 hours might be better. But you should be able to have no problem with that. Okay? Any questions then?
No.
Okay. I'm going to end the session now. And you guys, if you do have questions, I'll be here tomorrow. Technically, I think tomorrow's a holiday, but I'm going to be around. So make sure that you pose them to me, and also make sure you have some questions on Thursday if you need some stuff answered before the test, okay? But again, just chapter 8, chapter 9, and we'll be good to go, all right? All right, I'll get this formatted and posted, and I will see everybody on Thursday.